Hello, everyone, and welcome to the Activity 3 video key. Activity 3 is on continuing line structures, talking about functional groups, and also constitutional isomers. Let's start with part 1, identifying lone pairs and formal charge on line structures. So it says for each of the following molecules, draw in any lone pairs that are missing on the oxygen and or nitrogen atoms in order to complete the octet and determine if there is a formal charge present on those atoms. We need to add in lone pairs in order to get an octet, right? So this oxygen only has 2 electrons, so we need 3 sets of lone pairs to get a total of 8 electrons around it. It will have a negative charge when oxygen makes 1 bond with 3 lone pairs. Oxygen can make 2 bonds and have 2 lone pairs and be neutral. There's no formal charge on that oxygen. Nitrogen over here is making 3 bonds. When it does so, it also has 1 lone pair and it's neutral. Again, the calculation for formal charge is number of valence electrons minus the number of assigned electrons. So for example, for this nitrogen, 5 valence electrons minus 5 assigned electrons means we have no formal charge. For this nitrogen atom, we have 2 bonds, one to the hydrogen and one to this carbon. So we need 2 additional lone pairs for a total of 8 electrons to complete the octet. The nitrogen makes 2 bonds and has 2 lone pairs. It has a negative charge due to the calculation of 5 minus, in this case, 6 assigned electrons. Oxygen can make 3 bonds. When it does so, it has 1 lone pair and a formal positive charge. That's due to the calculation 6 valence electrons for oxygen minus, in this case, 5 assigned electrons equals +1 for the positive charge. Nitrogen can make 4 bonds. When it does so, it has a positive charge. We don't need to add any extra lone pairs here because nitrogen already has an octet when it makes 4 bonds. Moving on to part B, we want to draw in all of the hydrogen atoms and or lone pairs present. So the hydrogen atoms, there's just a bunch of them, right? And we can sort of start placing those in at every single carbon to make sure carbon is making a total of 4 bonds. And don't forget this carbon right here. The carbon that has a double bond needs 4 bonds as well, so it needs an additional bond to hydrogen. One here as well. Also, these methyls at the end are all CH3, so there's 3 hydrogens attached. Notice that this carbon has a positive charge. That means that it's electron deficient. It's not making 4 bonds. Instead, it's making 3 bonds. We call it a carbocation, and it has an empty p orbital. So it's missing an electron from its p orbital, and it's sp2 hybridized and trigonal planar. And so we don't need to draw a 4th bond to this carbon because, again, it's only making 3 bonds. And there's a missing electron, so we don't want to draw a lone pair there. Okay, moving on to this one, it's another carbocation. There are hydrogens all the way around the ring of the other carbons in order to make 4 bonds with each carbon. What about the carbon that's positively charged? It should be making 3 bonds, right, and have an empty orbital. So right now I can see 2 bonds, so I do need to draw in 1 additional bond to hydrogen. Let's look at this one. This carbon at the end here needs a 4th bond, so we'll draw in that bond to hydrogen. This one already has 4 bonds, so we don't need to draw in anything. The 2 that are participating in the double bond each have a hydrogen. And then this one at the end is a carbocation. Again, it's only making 3 bonds. So we should have 3 bonds total, which means 2 additional bonds to hydrogen and an empty orbital. Let's look at D. D is the only one that has a carbanion. Carbanions have a lone pair. They actually have that carbon has 4 electron groups. One of the electron groups is the lone pair, but the other 3 are bonds. So with one bond to another carbon being shown, there must be 2 additional bonds to hydrogen. And every other carbon where there isn't a charge, we just add enough hydrogens to make 4 bonds total to carbon. Let's move on to part 3, constitutional isomers. It says, in your own words, what are constitutional isomers? So in my words, they are 2 or more compounds that have the same molecular formula but different atom connectivity. Their atoms are connected in a different way, a different order, but they have the same molecular formula. So now we're going to practice drawing constitutional isomers. Part B says draw all line structures of the constitutional isomers that have the molecular formula of C4H9Br. Hint, there are 4 possible structures. So the hint is really helpful, so we don't just think, oh, could there be more? If we can get to 4, then we know that we're done. So what I would recommend doing is start with the hydrogen deficiency index. Right? So if we calculate the hydrogen deficiency index, we should get 0 or a whole number positive integer. So the calculation goes HDI is equal to 1/2 2 times the number of carbon, there's 4 carbons, so 8, plus 2, minus the number of hydrogen, and minus the number of halogens. Now it does say add the number of nitrogen in the formula, but there aren't any nitrogen. So we can do, 10 minus 10, 1/2 of 0 is 0. Right? So in this case, we know that the structure can have no pi bonds and no rings. And we do notice that there is a bromine. So I want you to think, based on the heteroatoms, what functional groups are possible given the HDI being 0 and the fact that we know that it has a bromine. Well, there's only one, right? Because there's only one function. There's 2 functional groups that include a halogen. Those are the acyl halide and the alkyl halide. Right, let's draw those in. Remind ourselves what it looked like. So functional groups, right, with a halogen. Those are the, and I'll just use X generically, right? In this case, it would be bromine, but it could be chlorine, something, a different halogen. Or we have the alkyl halide. We want to sort of know what functional group should I be going for. Right? Alkyl halide. So given the HDI is 0, right, this structure is not possible because in order to have a carbonyl, there is a pi bond in this structure. We already know that compounds with this molecular formula don't contain any pi bonds. So, and in addition, of course, we know that there's no oxygen in this formula. So an acyl halide is also impossible for that reason, right? So not possible without oxygen in the molecular formula and an HDI of equal to or greater than 1. And so this is the only possible functional group, okay, that we can think of when we're trying to draw our are constitutional isomers. Okay, so the other thing I want you to think about as well when you're trying to draw these, and I know it might seem unnecessary for this particular one because there's only 4 structures, it's not going to be too difficult to come up with them. But what if there were like 20, right? Then it would start to become more difficult. So then taking a systematic approach would be really important. So with C4, right, so I want you to now think about the 4 carbon sort of skeletal backbones, we call it. Right, so how can 4 carbons be attached to one another? Well, they could be attached to one another in a row, right? So 1, 2, 3, 4. That's possible. Or it's possible for there to be 3 carbons with a branch on the center carbon. That's another way to get 4 carbons attached. And then that's it. There aren't any other backbones. Because if I took off another carbon, right, then I would have to put it here, which would make the same thing, or put it here, which would make this. So there's only 2 skeletal backbones with 4 carbons, right? So we only have the 2 possibilities. Let's make sure we write that down. Only 2 possibilities. And that makes it really easy to be able to come in and draw the structures, right? Because basically we just have to think about, we're going to have no double bonds, no rings, 4 carbons. They're all going to have hydrogens attached to them, except for there'll be 1 bromine. So it's sort of, where can the bromine go, right? The bromine could go here, the bromine could go here. So we draw those structures. So we have, what if the bromine was at carbon number 1? And you can think of carbon number 1 as this one or this one, sort of, if you're counting this way or if you're counting that way. Maybe it goes at carbon number 1. Let's put it here. That's 1 structure. What if it goes at carbon number 2? That would make the structure. Those are different, right? Those have the formula that we're looking for. They have different atom connectivity. So they are constitutional isomers. What if I was to put the bromine here? That would actually just make the same compound as when I put it here. Because I can just start counting the other way. 1, 2 with the bromine here. This would be the same structure, just sort of flopped over, right, from this one. So try not to draw the same structure twice, right? And the way you can do that is think about like counting. 1, 2, 2, right? So it would be the same if you put the bromine here and here. It's just a different way of drawing it. So those are the only 2 that we can come up with this skeletal backbone. Right? So we'll call him the sort of the net here, right? For this particular skeletal backbone. All right, so what about the other skeletal backbone? Where can we put the bromine? Right, well, maybe we can put it on the center carbon, because remember, carbon can make 4 bonds. Right now it's making 3. We have a 4th one to bromine. We could also put it on one of these terminal positions here, and any one that we put it on would all be equivalent. Right, putting it here would be equivalent to putting it there. It would make the same structure. So try not to draw them twice again. We'll put it here, and then drawing that skeletal structure, you decide you want it to go here or here, here. Right? Doesn't matter. Let's put it here. Okay, so those are the other 2. Sort of make my little net around these 2 to show that those are part of this skeletal structure. So hopefully you can see that there is a systematic way of going about doing these problems. Let's try the next one. Now it says draw all, using line structures, of the constitutional isomers with the molecular formula C4H10O, what functional groups are possible? There's 7 possible structures. First, I'm going to I'll see what day it is. I'm going to use my phone so that it will focus. Fine, it not work. Okay, how about this page? Perfect. All right, I just want it to focus better so you guys can see it properly. Okay, so now we have a new molecular formula, right? Let's go ahead and calculate HDI. So HDI again, 1/2, 2 times the number of carbon, 8, plus 2 minus the number of hydrogen, and oxygens don't matter, right? So if there's oxygens, doesn't matter how many oxygens there are, if they are there, they don't go into the formula. They don't change the hydrogen deficiency index. So we will just go again. It's going to be 0, right? So no pi bonds and no rings. Okay, so what do we have in our formula, right? The only heteroatom we have is oxygen. So now we need to think, right? What are the possible functional groups? With 1 oxygen given an HDI of 0. So if the HDI was 1, there would be a lot more possibilities, because then you would have all the functional groups that include a carbonyl would be possible potentially, except for the ones that include more than 1 oxygen, like an ester. But we have an HDI of 0, right? So that means no pi bonds. So there's actually only 2 functional groups that don't contain a pi bond that do contain 1 oxygen. And those are the alcohol, right? So where we have the OH group, and we have an ether. So we have alcohol functional group and the ether group. Those are the only 2 that we can use. So that really narrows it down, right? We know sort of what functional groups we're going for. That's really helpful. And so, sorry, what did I do? Oh, yes, okay. So the next thing I wanted to do was the, again, the skeletal structures. Right? So we did that with C4 before, so we really don't have to do that again. We're just gonna remind ourselves, right, what the skeletal structures were. They were all 4 carbons in a row, or 3 in a row with a branch. So those are the 2 that we're going to be working with, and we're going to be trying to make alcohols and ethers with them. Okay, the alcohol is the easier one to do because the OH group will just go at the end somewhere, like at different positions, here, here, right? Kind of same thing we did before with the bromine, but we're going to put an OH instead of a bromine. So those are going to be fairly straightforward. It will just sort of 4 carbons in a row with an OH at the end. What about with an OH at carbon number 2, right? And then same thing here, we had put the OH in the center carbon or one of the end carbons. That comes up with 4, but we need 7 total. But that is all we can do in terms of alcohols, right? So what about ethers? So those are our 4 alcohols. So with ethers, it's a little bit more tricky because we need the oxygen to be in between 2 carbons, right? So we actually have to break these up. You have to sort of insert the carbon or the oxygen in between these 2 carbons or in between those 2 carbons, right, to make different structures. So that's a little bit more tricky. But we can think of, okay, where can we insert the oxygen? We can insert here, we can insert there. Those would give us 2 different ethers. go ahead and try to draw those. So if we're inserting, we just kind of go O in between those two carbons. And we can do that one as well. If we were to insert between these two, it would be the same as inserting. So we don't need to draw that twice. What about here? Are there any carbon-carbon bonds we can insert an oxygen in between? Well, technically, there's 3 different carbon-carbon bonds, and they're all equivalent. Okay, so it doesn't matter which one you pick. You insert an oxygen in between any one of those, it would all give us the same structure. So now we have a total of 7. We've got 4 alcohols and 3 ethers possible. Okay, moving on to part D. Draw all of the constitutional isomers with molecular formula C6H12 that possess 1 pi bond, don't include cyclic structures. Okay, well, let's go ahead and calculate the HDI anyway, even though they've given us a clue of what type of structures we should be using. So 1/2, 2 times the number of carbon, which is 6 carbon, 12 plus 2 minus the number of hydrogen, 12. There's nothing else in the formula. So now we're going to have 1/2 of 2. So this tells us that we should have 1 ring or 1 pi bond, but it says they only include those that have a pi bond. They don't include cyclic structures. So our 1 is going to be the pi bond. There are cyclic structures that will match this formula. The goal is just not to worry about those because that's what the question asked for. And telling us, of course, our target. This is the one that students struggle with the most because there's so many possibilities and students inevitably end up drawing the same thing more than once without realizing that. So it's really important to be systematic, right? And to use our skeletal structures to our advantage to generate the 13 possible structures. Okay, first of all, we don't have any heteroatoms in the structure. There's no nitrogen, oxygen, or halogens. So we're just dealing with carbon and hydrogen, right? So the functional groups that just have carbon and hydrogen, right, with a pi bond, there's only 1 functional group. That's an alkene, right? So all of the structures will have to be alkenes, because that's the only functional group that only contains 1 pi bond that only contains carbon and hydrogen. And so we'll be trying to go for those carbon double bonded carbon structures. Okay, but we can still use our skeletal structures, right? But now we have to generate a list using 6 carbons, right? So what are the possible skeletal backbones with 6 carbons? That's the question we're asking ourselves. So of course we can have all 6 carbons attached in a row. So we just draw linearly a zigzag for 6 total carbons. Okay, what else? Maybe we have some branching. So I sort of take one off the end and put it somewhere where it could form a branch. So if we take one off the end, then we'll be at 5 carbons in the linear chain, right, with perhaps a branch there. Or alternately, we could branch at the sister carbon. Okay, so here's another one, 5 carbons. So that's a different skeletal backbone in this one. If I was to take that methyl and put it here, then that's just the same thing as this flipped over. So I don't want to do that. So that's 5 carbons in a row with some branching. What about 4 carbons in a row? Right? Is that possible? If you have 4 carbons in a row, now you need 2 branches. Okay, where are those 2 branches going to go? Maybe one is going to go here and one's going to go there. It's a possibility. And what about 4 carbons in a row with 2 branches on the same carbon? Is that a possibility? So maybe you go here and here. Okay, so that's a possibility. That's the only way we can do 4 carbons in a row with 2 branches, right? Because if I take this one and move it over here, that's the same as that structure. So no difference. If I did 3 carbons in a row, I would need 3 branches, and that's not possible without adding to the 3 carbon chain. These are what we believe to be our possible skeletal backbones. Now we just need to add a pi bond everywhere we can add a pi bond that would make a different structure. So let's say with A, I'm going to make these, I'm going to do these in orange, right? So we have 6 carbons in a row and put in a double bond. Maybe I put it in at the end here. So it's possible that I could have 6 carbons in a row. The double bond could be here. And lastly, carbons in a row with the double bond there. If I keep going, I'm going to end up, if I put the double bond here, I'll end up with the structure. It's flipped over. Okay, so that's not very helpful. So only 3 with this skeletal backbone. Let's move on to another skeletal backbone. Right, how about this one? This one B. Let's draw that and put the double bond everywhere possibly. Double bond. Right? So we just sort of work our way from one end to the other. Here we put the double bond here. And draw that skeletal backbone again. Maybe it goes here. We can keep going. Maybe it goes there. And then one more. Maybe it goes, so you can put the last one or here or here. Right? Those would be equivalent. Doesn't matter if it goes here. That would have been the same as putting it here. You just sort of rotate around the bond and it's the same thing. So again, it's really tricky to try not to do the same thing twice. Okay, so only 4 for that one. What about, let's do this structure next. So we do 1, 2, 3, 4, 5. Figure out all the different places. Maybe start at the end here and here and then here. Right? If I go any further, I'll be repeating structures. So we're only at 3 for that one. Let's do this with D. Let's draw that skeletal structure out. Where can I place a double bond, right? So place it here or here or here or here. Those are all the same thing. Just pick one. It doesn't matter. There would have been the same as putting double bond here or there, just because of the symmetry of this. So the only other place on that skeletal backbone that's different is this one. Then we just have one more. We'll call this E. So I'll be able to draw this over here. And then ask myself, where can I place the double bond? Well, there's actually only one place, and that's here. The reason for that is because I can't place a double bond here. That would make 5 bonds to this carbon. Remember, that's one of our cardinal rules. You cannot make 5 bonds to carbon. That's not possible. So any double bond involving this carbon, whether it's here, 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 or here, would mean that this carbon has 5 bonds. So that's not a possible structure. So that's it. Let's make sure we got 13. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. So systematically, we were able to get the right number without, missing any. Okay. Let's start talking about functional groups. Right. So it says to basically just identify functional groups. Hopefully, everybody's watched the lab lecture. I talk about some tips here for identifying functional groups. Sometimes people think there's way too many, right? If they, for example, think this is a ketone, right, and an alcohol and a carboxylic acid, that's not. when the carbon has both a carbonyl and an OH, the whole thing is just a carboxylic acid. It is not a ketone and an alcohol and a carboxylic acid. If that doesn't make sense, maybe try watching that pre-lab lecture video one more time. I'm going to label this as a carboxylic acid. Right, and then down here, where this one jumps out at you, an alkyne. And then this nitrogen is attached to a carbon that does not have a carbonyl, called an amine. And then up here, we have a carbon with a carbonyl attached to an oxygen that's attached to another carbon. That's an ester. And actually, we have another amine. Right? Now we have this nitrogen attached to a carbon, also attached to two other carbons, but it's still an amine, just like this carbonyl up here. The carbon is attached to two carbons. So that means that this is a ketone. This nitrogen is attached to a carbon that has a carbonyl. This is not an amine. Instead, it's an amide. People call it an amide. And here we have a double bond. There's not 3 double bonds and a 6-member ring, just the 1 double bond. Right, so this is an alkene, which is contrasted with this ring, right, which has 3 alternating double bonds. This is an aromatic. Over here, we have a carbon. It's part of a carbonyl attached to a carbon on one side and a hydrogen on the other side. This is an aldehyde. And then lastly, we have a oxygen that's attached to carbon on both sides. Neither carbon has a carbonyl, so it is. On to the next one. Let's see what we can find here. So we have a carbon attached to a carbonyl, an oxygen, double bonded to an oxygen, that's a carbonyl, also attached to a halogen. This is acyl halide. Okay, let's compare that to this bromine that's attached to a carbon that does not have a carbonyl. This means that this is alkyl halide. We have in sulfur attached to a carbon and a hydrogen, thiol. And we have 2 double bonds. They're both alkenes, or actually when they're right next to each other, they're called a diene. But don't worry about that. We haven't covered that yet. That'll be talked about much later in the year of organic chemistry. Okay, what about this nitrogen right here that's attached to carbons, no carbonyl next to it, and also 1 hydrogen. This is the amine. Here we have an ester. And a ketone. two carbonyls with an oxygen in between. You recognize this as an anhydride. Anhydride. And of course, this ring in the center, pretty crowded in here. That's where the colors come in to really help you see the difference. That aromatic ring. Up here, I've got a carbonyl next to a nitrogen. This is an amide. And I have a carbon attached to an OH, a carbonyl here, so this is an alcohol. And I've got an oxygen sandwiched in between two carbons. This is an ether. And then we have a sulfur in between two carbons. This is a sulfide. And that was a lot, but we got them all. Move on to the last part. As for each of the following, draw a line structure of a molecule that contains the given functional groups and is consistent with the given molecular formula. Calculate the HDI and label the functional groups. Okay, so it wants us to calculate the HDI. Go ahead and do that. HDI is 1/2, 2 times the number of carbons, 6 plus 2, minus the number of hydrogen, H, minus 4, the number of hydrogen, minus the number of halogens, oxygens, don't count. We have 8 minus 6, 2, 1/2. So only one unit of unsaturation. And the acyl halide has 1 pi bond. So it makes sense that that unit of unsaturation, or that unit in the hydrogen deficiency index, will be part of the acyl halide. Okay, so the goal here is to get 3 carbons, right? And these different functional groups. Let's remind ourselves what these functional groups look like before we try to assemble it into a structure. We've got an alkyl halide, which is a carbon attached to a halogen, which in this case has to be chlorine. Right? We've got our acyl halide, which is a carbon that has a carbonyl and halogen directly attached. And then the alcohol, which is a carbon OH attached to it. So that's sort of our goal, and you can kind of use up all 3 carbons that we have. So we're going to start with carbon 1, right? And you sort of decide what you want it to be. Maybe it's going to be the acyl halide. That. And then attached to a carbon that maybe it has the alcohol. Or it could have been the halogen for the alkyl halide. We have our next carbon, which is going to have a halogen. Right, so there's a bunch of possibilities that you could have come up with. This isn't the only possible answer. Right, so I'll just put one possible answer. Would be this one. Right, we have our halide. Have alcohol. Alkyl. Okay. Moving on to the next structure. Calculate that HDI. The HDI here is 1/2. 2 times 6 is 12. It's 2 minus 15 plus 1 for the nitrogen. And sulfur, that's a tricky one because that didn't technically go in the formula. But look at where sulfur is on the periodic table, right below oxygen. So it's likely that it's not going to affect HDI. Just assume it doesn't, calculate it and see what happens. So we have 14 15 minus 15, 0. So we ended up with 0. Well, let's look at our functional groups and see if it's possible to have an HDI of 0. So the thiol is a carbon attached to a sulfur attached to hydrogen. So no problem there. And then the amine is just a nitrogen attached to at least one carbon, possibly up to 3 carbons, right, for hydrogen. So next we get hydrogen carbon, hydrogen of carbon. But nitrogen needs to be at least one carbon, otherwise it wouldn't be an organic structure. It would just be ammonia, which is technically not organic. Again, you don't have to have a pi bond here for an amine, so that's good. And then of course the alcohol is the COH, so no problem. So it looks like we should be able to draw a structure without any HDI, so we probably okay. So let's go ahead and draw in 6 carbons. And the easiest way, we don't have any ether, right, which would sort of break up the carbon chain. All of these, it looks like, it's possible it could come at the end. The nitrogen is the only one that could come sort of in between. We'll draw a few possible structures. We could have 6 carbons in a row, right? And then let's say on one carbon, we have the SH group, and that will give us our thiol. On another carbon, just try not to make it the same carbon because you don't want to bunch up your functional groups. Likely that they're not going to share the same. So maybe somewhere else we'll put an alcohol. And then in amine, since I already used up all my 6 carbons, I would just probably want to make an NH2 somewhere, so I don't add any additional carbons. So perhaps anywhere, just put here in NH2. So this is one possibility. We have an amine, we have thiol, and we have an alcohol. Of course, you would want to double check that it matches the formula. Especially with the amine, because that one could have multiple carbons. So if we sort of start with the nitrogen, like what if the carbons are attached to it? So look at these 1, 2, 3, 4, 5. You get something like that for 6 carbons. That's a possibility. This is still an amine. This is still an amine. So now we just need to add the thiol and the alcohol. So, and we could add those anywhere. Try to space them out is all I would say, because that's more likely structure. There, thiol there. Alcohol. And okay, so we'll say, when I just make that clear. When I said one possible answer, I didn't mean that there's only one possible answer. I just meant that this is one of multiple possibilities. Okay? So one possible answer, there are other correct answers. I want to make that super clear. Okay, here's 2 possible answers, many other possibilities. Okay, moving on to the last one here, let's calculate the HDI. 1/2, 2 times the number of carbon, which is 16, plus 2 minus the number of hydrogen, which is 6. Oxygen count. So now we have 18 minus 6 is 12. 1/2 of 12 is 6. So we have a very high unit of unsaturation, which means that we are going to have lots of rings or pi bonds. Right? So if I look here, I've got the aromatic ring That's actually makes a lot of sense because the aromatic ring, there's a ring, right? So that's one. Then there's 3 pi bonds. That's 3 more. So this by itself takes into account an HDI of 4. So now we only have 2 more. The aldehyde will be a carbon, carbonyl, carbon attached, and hydrogen attached on the other side. So that's an HDI of 1. This is the pi bond. Okay, and then the carboxylic acid is the carbon, the carbonyl, OH, one side and a carbon on the other side. So this is also an HDI of 1. So it makes sense then, if we have all 3 of these functional groups, that we have an HDI of 6. Okay, so let's start drawing our structure. Sort of start with the aromatic ring because we know exactly what that's going to look like. Right, and then maybe attach to something. Right, let's add in the aldehyde. Line structure, I'm going to omit the C. Okay, and I'm just going to draw in the carbonyl. It's optional to draw in the hydrogen attached to the carbon for the aldehyde. This is optional to draw in as the line structure. I like to do it. It makes it really clear that it's an aldehyde to me. Like I just didn't forget to put something else there. So, but it, again, it's optional. And then we also have a carboxylic acid. So I'm probably going to place that somewhere else on the group. Maybe it could be here, it could be here, it could be here. They're all anywhere really. You could do so carbonyl and OH. And now we have our 8 carbons, 3 oxygens, 6 hydrogens. This is just one, again, one possibility, multiple possibilities here. Aldehyde. Aromatic ring. And carboxylic acid. And then I'll just make a note, right? Other possible structures. Okay. Hopefully that helped. If you were struggling at any point during the activity, if not, keep up the good work, and hopefully I will see you or talk to you very soon.